Hello, everybody. Woo! That was too much. Let's see. 1, 2, 3. Still too much. 1, 2, 3. That's better, huh? Okay. Let me tell you what I have planned for you today. I'm going to go back to the geometric random variable and talk about one of its most important properties, which is the memorylessness property. Or memoryless property. And I'll define what I mean by that. And then I will talk about the expected value. No, actually, before I do that, I have to talk about the law of total expectation. This is more general than I should put this outside. So this would be a bullet item of its own. And once we have the law of total expectation, we can talk about the expected value of the geometric. Okay? And then, once we nail down the geometric random variable, I'm going to talk about a cool problem called the coupon collector's problem. Which is related to the geometric, but not as simple as the geometric. And then, depending on how we're doing with time, I will talk about the Poisson random variable or variance. The concept of variance. So we've studied the concept of, and also standard deviation. That's my plan. I might have to swap these two depending on how we're doing with time, because Poisson can possibly wait till the next lecture. I don't want to delay variance until the next lecture. Okay? All right. So, let's go back to the geometric. Random variable. I may not have talked about this explicitly last time, but there's an angle you can look at the geometric that might be more palatable to you. So remember, the underlying process is a Bernoulli process, a Bernoulli trial. You have coin flips. It's amazing how many different areas of probability theory coin flips come into the picture in. So you have a coin, it's biased, it has probability P of turning up heads, in which case we mark a 1. And with probability 1 minus P, it's a 0. So if I keep flipping this coin independently, I can look at the outcome in a couple of different ways at least. One is I can write down a string of bits. So every time I get a head, I mark a 1. And every time I get a tail, I mark a 0. Okay? And I may get some sequence like that. Okay, so this is a string of bits. Another way I can look at it is by creating a function whose values at various points are random. So I have this function of a discrete variable, n, which I'm going to refer to as time in this case. I create this function of n. Every time I have a head, I draw a lollipop of height 1. And every time I have a tail, I put just a little circle at 0. So I have, if I want to map it to what I drew above, then I can't have that here. So I will have 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, and so on. Okay? Now, unlike the ordinary functions or deterministic functions that you're used to, this function is random. And notice I've used the capital letter X to represent it. So this function is random because at various points along the time axis, you never know what exactly is going to be the outcome unless I give you the outcome of the experiment. So you don't know a priori what sequence of ones and zeros you're going to get. And so there are different manifestations of this process, each with its own probability. So there's a whole family of such functions with these lollipops scattered all over the place, depending on what the outcome of the coin flips were. So this we call a random process. And this random process is created by a sequence of Bernoulli trials, coin flips. Now, getting back to the geometric random variable, we said the geometric random variable is the time until, from the start of the coin flipping, the time until the first head, say, okay, or the first success, or in this case, the first one. So let me grab a different color. Well, don't do that. Where'd all my colors go? I'll use that one. Oh, that's a highlighter. I need an edX course just to handle this thing. Okay, let's try this. Notice this distance from a 1 to the next one. If I were to ask you, describe the probability law governing the number of flips from this one here until and including the next one. So I have flipped the coin, I've got a head. I'm right here. It has occurred already. And now I ask you, what's the probability law governing the number of flips I have to do to get to the next head? What is that random variable? Geometric. That's exactly what this is. So you get a sequence of failures, air quotes, until you get the next one. So in this case, it happened to occur on the first, second, third, fourth flip. Then I look at the next distance between subsequent ones, and it just so happened that the first flip after the one after this one ended up being a head, so I marked that as a 1. Okay, so that's why we also refer to this as a first order. This is probably not a good color for that. Inter-arrival time of a Bernoulli process. That's what a geometric random variable is. That's one way to look at it. A geometric random variable can be thought of as the first order inter-arrival time. By arrival, we mean the arrival of a 1, or the occurrence of a head, or the occurrence of a success. Okay, however you want to define it. The distance between successes without any other intermediary success is called the first order inter-arrival time. If I wanted to measure the second order inter-arrival time, then I would have to hop over 1, 1. Right? So the second order inter-arrival time would be from here to this guy. Okay, so the geometric random variable can be thought of as the first order inter-arrival time between these ones. And we specified that last time. I think I used the variable L. I'm again going to use the full notation so that whichever you're comfortable with, you can use. So the random variable L is geometric if it obeys which probability law? How do I write that? How many failures do I have before I have my first success? Louder, everybody. L minus 1. And each of those occurs with probability 1 minus P. Immediately after I have my L minus 1 failures, I have a success. And that happens with probability P. And of course, this random variable. I can't have my first success on the 0th flip. I can, at the earliest, get it on the first flip. So this is how we define it, and it's 0 elsewhere. Another way we sometimes designate the geometric random variable is in this way, or by simply saying it's a geometric with parameter p. In other words, the underlying Bernoulli process that defines this geometric random variable has probability p of success. These are various ways of describing the same thing. Okay. Any questions on what I've said so far? There's nothing earth-shattering in what I've said. There's really nothing new, except perhaps the definition of first-order interarrival times. Good to go? Okay. So, now, let's use a concrete context to describe this, what I said is the memorylessness property of the geometric random variable. Suppose this random variable describes the lifetime of a bulb where the bulb, so let's give it some context. So we have a bulb. L is its lifetime. In hours. Okay? And so, let's draw a timeline here. I have 1, 2, 3, 4, and so on. And I say that the lifetime of the bulb is 1 if somehow it conks out in this interval, starting at 1 and right before 2. So, L is equal to L if the bulb dies in the interval L square bracket L plus 1 parenthesis. Okay? Are we clear? The light bulb lasts L hours if it dies between the Lth hour and right before the L plus first hour. Okay. Now, and suppose it dies with probability P, it dies in any given hour. With 1 minus P, it does not die. Yeah. Now, this is my first interval from 1 to 2. Starting at 1, I'm starting here at 1. This is my first hour. So what I've labeled it as 1 is actually time, real time t equals 0 until the 59th and 59th second. Okay? Yeah. Okay. So with probability P, bulb dies. So what do we have? We have a sequence of Bernoulli trials. Every hour, there's the same probability P that this bulb may die. What is the probability law governing the light bulb? I saved trick questions for the midterm. Geometric. Although I found out yesterday in my 120 office hours from a student who's taking both courses with me that the mean was atrocious. Is that true? There's going to be some firefights at the staff meetings. I apologize. I don't know why I have to keep apologizing for all. So that's the lifetime of the bulb. All right. Now, I come to you and I say, the bulb has survived W hours. suppose the bulb has survived W hours. In other words, it did not die on the Wth time interval. So, let's draw the timeline again. I've got 1, and this is W, and this is W plus 1. This dude has survived W hours. Okay? What is the probability that it will survive? What happened to the L more hours? In other words, it dies in this interval. That's my question. Okay, good. Because I don't want you to give me an answer.
So, we don't know if the bulb died.
We know that it did not die in the green interval. We are now asking the question, what is the probability that it will last another L hours? Small L hours. Question? We know P. Yeah. P is fixed. Okay? So this is essentially, so I've conditioned my space. I hope you realize that we've conditioned our space. What is the conditioning event? I'm trying to compute some probability given some event. What is that event? Capital L is what? By the way, I'm using W here as a mnemonic. It's like waiting time or wasted flips. If you're doing, you can also bring in a gambling context to this. You and your friend are making a bet, and the first heads, somebody wins, and somebody's flipped the coin W times, and no head has shown up. Does that increase or decrease the likelihood of a head occurring at the next flip? That's kind of that flavor. So what is the conditioning event? If the bulb has already survived W hours, what should I put here? Greater than W. That's my conditioning event. Okay? Because it has survived at least W hours. And now, I want to compute the probability that the total lifetime of the bulb is W plus small l. Is the setup clear? If you get lost here, you're going to lose me for the rest of the whole discussion, and you're going to lose me for coupon collector's problem, and we don't want that. Is the setup clear? Okay, cool. Now I'm here to tell you we claim that the probability is exactly that. Yeah. L equals W means it died on the Wth hour. But it did not die until, So it may die on the W plus first hour. We don't know when it's going to die after this. Yeah, that's exactly the kind of question, clarifying question I hope you guys ask so that we don't run into trouble. Okay. This is called the memorylessness property, or memoryless property of the geometric. In other words, the fact that the bulb has survived W hours does not affect its remaining lifetime. That's what it says. Question? No, because L is the total lifetime from here to here.
Yeah, but you just said that given that it survives W hours,
Uh-huh.
does not affect the probability that it will have L more hours.
Yeah, small L more hours. So from here to here is small L. From here to here it's W. The total lifetime is capital L, which is small l plus small w.
But that would mean that you would have a less likelihood of finding it given that W is large as opposed to W.
No, that's the whole point. That's exactly the whole point. That it's not less likely that it will die sooner. That's what the memorylessness property is all about. That's why it's counterintuitive. So, why don't you give me a moment to derive the probability law, and then you'll see where the rescaling occurs and what the shift is that happens, and then if you still have the same question, I'll address it. Yeah. I can't hear you, Rohan. Capital L is the total lifetime of the bulb. Right? Starting here, ending wherever it dies. P of L, what? You want L here? But the way I've defined the two non-overlapping intervals, it can't be small l here. So you can look at it in a different way. You can look at this as the same as the probability that the total lifetime minus W is L. That's another way to look at it. If that's more comfortable for you, feel free to do that. In other words, I've spent W hours, and now the remaining lifetime is small l. Okay? So that means the total lifetime minus the waiting time is the remaining lifetime. Maybe I have a typo here. Do I have a typo? Is that why it's... I don't think so. I don't believe so. So, total lifetime is W plus L. That's the conditioning event. And the total lifetime's likelihood that it's equal to this total is not affected by the fact that it's greater than W. No, that's correct. I think the source of the confusion is you are measuring capital L from here to here. That's not what I'm doing. Capital L is still the total lifetime of the bulb. Jack. Okay, let's go through the process and we'll see. Okay? Just bear with me. So, give me the conditional probability law. What's the definition? Let's do it step by step. If I end up having the wrong expression here, we'll correct it at the end, okay? We'll start with the left side. Do you agree with the left side that that's what I'm trying to calculate? Okay, so let's start with where we agree. All right, so this is what? What's in the denominator? Greater than W. That's my conditioning event. Okay? So I'm scaling all the probabilities by the probability of the conditioning event. I like this. This is kind of a quasi-democracy here. Didn't expect Sproul kind of activity from the nerds of the campus. Ouch! Very good, very good. Each generation is an improvement over the previous one. All right, so what do I have in the numerator? Two events, right? L is equal to W plus L, and L is more than W. All right. So we did this sort of last time. Here's my original probability. Here's PL, and it's a geometric. It keeps decaying exponentially. It starts at 1. Okay? This is the unconditional probability. And we started with P, 1 minus P times P, 1 minus P squared times P. At some point, I'm at W. Okay? And then I have W plus 1. So what is so dot, dot, dot. And what is this one? 1 minus P to the what? W. No? Minus 1 times P. And this one is 1 minus P to the W times P. And it continues to decay. Correct? So what are the points corresponding to the intersection of the conditioning event? Basically, the top, this part, right here. How would I clean up this probability law? So everything now has to start from W. Okay? So now we have, I'm going to rescale, because otherwise I'll have to put minuscule bars. So, no, everything now starts at? No, not W. W plus 1. W plus 2. And so on. Okay? Now what was the original value of the lollipop at W plus 1? It's right here. 1 minus P to the W times P. I have to divide that. Let's do that in color. I have to divide that by what? P of L greater than W. And I've got to do the same thing with all the other lollipops, correct? Isn't that what the denominator here says? Okay. So now the question is, what is P of L greater than W? And that's where you come in. Oops. That's not that. What is P of L greater than W? I want you to work with your neighbors and compute that probability. Which lollipops in the original probability law do you have to add up to compute this probability? Can you tell me? Tell your neighbor. And get back to me in about a minute. If you don't know your neighbor, please introduce yourselves. You got to get comfortable with each other. You'll be talking quite a bit. Okay. Rohan. Yeah, up to you to pass or to take. Okay. Walk me through it. Don't give me a final answer. Well, I want to compute it from this probability mass function. Yeah, I'm summing over these L's, right? W plus 1 to infinity of to the L minus 1 times P. That's my probability mass function. I'm summing it over the appropriate points. The appropriate points are from W plus 1 all the way to infinity. Okay? So this P doesn't belong there. We pull it out. And can you tell me how to figure out this power series? As a geometric series. Yep. Can I create a corner of useless information here? And let's just... Here's a corner of useless information. I've got alpha to the L. L equals A to B. And if alpha is not equal to 1, this is going to be alpha to the B plus 1 minus alpha to the A over alpha minus 1. Okay? Now, if alpha is less than... And we also know... we can use this one. If alpha is less than 1, I can make one of the limits infinity, the B infinity. Okay? What happens if I make B infinity, and my alpha here is 1 minus P? So, can you give me the... If I make B infinity, what happens to this term? Goes to 0. Why? Because 1 minus P is less than 1. When you raise something that's less than 1 to infinity, you get 0. Minus alpha to the A, lower limit, which is what? 1 minus P to the W plus 1 minus 1. So it's W divided by alpha minus 1. So what do you get? These ones cancel. This P and this P cancels. 1 minus P to the W. All right, so now we know what to put here. If I divide by 1 minus P to the W, what do I get? Notice the red here? That's what I'm dividing by. That's what I just computed. So what happens when I divide this guy here by 1 minus P to the W? I get P. So let's zap that out. Actually, let me redraw. So I'm going to... Oh, come on. Where's my black? Oh, here we go. They're all hiding there. So starting at W plus 1, I now have a P. What's the next one? The next one will be 1 plus 1 power higher, right? 1 minus P times P. So when you compare this with the original, so this is P of L, given that L is greater than W of L. How does this compare with the original PMF? What was the original PMF? Wasn't it just this shape starting at 1? So what have we done to it? No, we've done something to it. We've just shifted it. All the lollipops just got shifted to the right by W. What's the expected remaining lifetime? Is it different from a brand new bulb? No. So now I want to make sure. So this is the probability that L is. Oh, now I understand why there's confusion here. Okay, I agree with you with this expression here. Hey, I said once we go through the derivation, it's not touchy-feely humanities, social science. We go through the derivation. If the answer ends up showing that I'm wrong, I say I'm wrong. There we go. So we figured it out. But the important thing, folks, is this. This is the critical part. The fact that the light bulb has survived W hours does not change the remaining lifetime's probability law. Okay? If I bring an identical light bulb and turn it on at the W plus first hour and let these two bulbs run, there is no reason to expect that the first bulb will die earlier than the brand new bulb that you brought in at the hour W plus 1. That's the point. And there are two probability laws that we study in this course that have this property. One is the geometric for the in the discrete realm. And then later on, when we go to the continuous random variables, its counterpart will be the exponential random variable. That random variable too will have this property. Okay. So without knowing anything else about what the expected value of the geometric random variable is, if I were to tell you that the bulb has survived W hours, what's the total expected lifetime of the bulb given that it has survived W hours? What would you tell me? Let's go back to the original time axis. Here. It has already spent W hours. That's fixed. You're given that, right? Jack. So I'm not asking for the probability, I'm asking for the expected total lifetime. Let me rephrase. What's the expected remaining lifetime? I haven't figured out what it is, but it's expected value of L, right? So if it has already survived W hours and the remaining lifetime has an expectancy of E of capital L, what's the total expected value? The sum of them. Exactly. So this is simply W added to whatever the original a priori expected length was. I haven't figured that out yet. Okay. So now if we're talking about coin flips, heads and tails, yeah. So the question was, what's in real life that has these kinds of characteristics? Practically nothing, but we model. No. It's hold on. In the real world, we're always dealing with models. Some models under certain assumptions are good enough, and they do pretty well. The other random variable that I'm going to discuss, which is the Poisson, builds on top of the Bernoulli and the binomial, and it models any process where you have Bernoulli trials where the probabilities are extremely lopsided. So, for example, if you want to figure out the number of people who drive out their cars in San Francisco, and by the time they get back in the evening, they have experienced the car accident, that's a Bernoulli trial, where the probability of a car accident is extremely low compared to coming back home safe and sound, right? And now you have thousands upon thousands of these repetitions, so each person, if you assume that they're independent, then you've got a sum that is a binomial that you can represent exactly as a binomial, and then you can approximate as a Poisson. Modeling and approximation is part and parcel of engineering and real world. Okay, but these are toy problems on which we build much more complex models. Very good question. Okay, now I want to figure out what this E of L is. So what is this E of L? What is the expected value of a geometric? Let's go back to coin flips. I need one more tool to be able to answer this question. And that one additional tool is called the law of total expectation. And it's basically a corollary of the law of total probability. I have a universe that I'm going to split into a set of events that are mutually exclusive and collectively exhaustive. What do you know about the probability of some event B in terms of, so if I have, let's say I have an event B, what was our divide and conquer method for figuring out this probability? Sum of what? B intersect the AIs, right? Over all i's. And the one twist that we didn't do after we studied conditional probability is that we can write this in terms of a conditional probability. I can write these joints as the probability of B given AI times what? Probability of AI. These are equivalent ways of writing the same probability. Okay, this is from eons ago. Now we use this to develop the expected value form that's derived from this law of total probability. Remember, the expected value of a random variable is the sum over all x of px of x, right? That was our definition of the expected value. And the law of total probability tells me that I can write px as a bunch of conditionals. Pi. Correct? Are you all with me? Now I just plug this in here. So I have summation over x, small x. Now instead of pxx, I have summation over I, p of x given ai, x, p, ai. And now, like any self-respecting engineer, I unscrupulously change the order of the summations, since shivers down our mathematician colleagues' spines. And what do you think this is? All I have done is conditioned the space on the event AI. Talk to your neighbor and see how I should define that. If this is the unconditional expected value, what do you think this is? What am I weighting by? How do you compare these two? Notice the format is the same, no? It's a conditional expected value. This is simply E of x given AI. So, now we have the counterpart of the law of total probability for expected values. This is the law of total expectation. Rohan, did you have a question? The switching? Yeah, we just do that. because in the real world, it's not going to be an issue. The cases where you can't switch are when you have infinite sums and what's inside is something pathological. Not just countable finite set. Even when we get to continuous probability, if you have two integrals that go from minus infinity to infinity, in this class, don't worry about it. Just swap if you have to. Yeah, because probabilities have to die out, right? They have to die out fast enough so that the sum over all the lollipops, or in the case of continuous probability density functions, the integral over the probability has to be 1. So the issue of swapping is never a problem. All right, now why did I do this? Why are we studying this law of conditional probability? This is another one of those tools in your arsenal of divide and conquer. So if you can find just the right conditioning events that will make your problem simple, then do that. Notice if I want to, now let's go back to the geometric. If I want to figure out the mean of the geometric by simply plugging it into the definition, I would have a sum going from where to where? L goes from 1 to infinity of small l, P, L, L. This is what I would have to do if I wanted to figure out the whole thing on its own. So this is what you'd have to do. L, 1 minus P to the L minus 1 times P. It's not too bad if you're going to use differentiation and things like that, but it's not very clean. So this is doable, but not pretty. So here's what I'm going to do. Alternative. I am going to split my space not into A1, A2, A3, AN, but I'm going to split my space. Let's draw the sample space again. So I might get a head on the first trial, or a tail on the first trial. Or I might get my head on the second trial, or a tail on the second trial, and so on. And whenever I get my first head, that's where I stop. That's why the upper branches don't continue. If I get a head, I stop there. I am going to split my universe into two non-overlapping events. And those two events are the events that constitute the result of the very first flip. I either get a head on the first flip or I get a tail on the first flip. Are you all with me? There's no third possibility, right? When I run this trial, one way to split my sample space is based on the result of the first flip. If my first flip is a head, that's this side. If it's a tail, it's this side, mutually exclusive, collectively exhaustive. Okay? In other words, what we've done is split the sample space into this event and I need a highlighter. Is that a highlighter? And everything else goes under T1. That's how I've split my sample points. Okay. Now, the law of total expectation says, oh no, not that one. The law of total expectation says, why is it giving me brown here? Black. So based on this splitting, how can I write the total, the expected value of L? L given, come on people, H1 times P of H1 plus E of L given H2, T1 times the probability of T1. So I use the law of total expectation to split this into two terms based on the result of the very first flip. What is P of H1? Everybody. P. And this is 1 minus P. Now, here's a slightly tricky question. What's the expected value of L if the first flip is ahead? 1. Exactly. If the first flip was ahead, L is 1. Right? In fact, I can write the probability law for that case, and it's just a single lollipop of strength 1 at 1. Everything else is 0. Anytime you have a single lollipop, you're talking about a deterministic number. Once I tell you the first flip was ahead, in your conditional universe, L is fixed. It's 1. It's done. Okay? So this is 1. What is this? Tell your neighbor. Don't tell me. We've answered this already up here. If you go back in your notes, right here. What is W in this case? Huh? Louder. 1. So this is, give me the expression for this then. 1 plus E of L. Oh, you must have an excellent probability instructor. So, now we have an equation for E of L. I have E of L on the left side, right here. And on the right side, I have P times 1, P, plus 1 times 1 minus P. So that's 1 minus P, plus E of L times 1 minus P. Can you solve this for E of L for me, please, and tell me what you get? Talk to each other, people. Talk to each other. There's enough of you. By the way, I'm glad more of you are showing up. Thank you. What do you get for E of L? If I don't get to the coupon collector problem, Satish is going to shoot me. 1 over P. If you solve for E of L. Now, let's do an intuitive interpretation of this result. So, let's backtrack a bit. We use the law of total expectation to do a divide and conquer, and we split our sample space into two very simple, non-overlapping events. Namely, the result of the first flip. So the first flip is either ahead, in which case L is 1, we're done. Or it's a tail, in which case we're back to square 1. And it's as if you just started flipping. You just wasted a flip. Hence the letter W. Or you just waited out a flip. Hence the letter W. Equals 1 in this case. So if you have waited one flip, and based on memorylessness, you know that the expected number of flips until the first head is no different from another poor slob who shows up here next to you with an identical coin and flips it, then it's going to be 1 plus E of L. So you have two things, two E of L's on the two sides. You solve for it, you get 1 over P. Now we have to make sure that this answer makes sense. If P is small, if the probability of a head is small, what do you expect in terms of the number of flips that you have to endure? It has to be larger, right? So if P is small, the probability of a head on any given flip is small, then obviously you expect to wait longer. You have to do more flips before you get your first head. And similarly, if the probability of head is large, then you don't have to wait as long to get, on average, to get your first flip. So this answer makes sense. Any questions on what we did? Yeah. So, remember, so in this case, we're dealing with the W equals 1 case here, right? So you've taken the probability mass function and you've just shifted it to the right by 1. Where is the new center of gravity of those masses? Whatever it was before, which was E of L, which we're trying to find, plus 1. That's it. Yeah. Okay. Now, let's get to the coupon collectors problem. Actually, why don't you take a break? I think you need a break. Okay, let's resume. So this problem originated, according to legend, with a cereal manufacturer producing boxes of cereal in which there was a coupon. One of n distinct coupons was randomly placed in the cereal box. And so we have n distinct coupons. One randomly selected. By that we mean equally likely selected for each box. And the question is, on average, how many cereal boxes do you have to buy until you collect all n distinct coupons? So let's call that L, number of boxes you collect or you purchase. Up to and including first nth distinct coupon. Okay? Another way of phrasing this is you have an urn. In this urn there are n distinct balls. You keep sticking your hand in the urn. You yank a ball at random and you look at it. If it's new, you mark that down. You put it down. And so you replace the ball and you put it back in the urn and you stick your hand in there again and pull another one out. How many times do you have to do this on average to get all n balls? Okay? So, what is L1? Number of draws until the first distinct ball. Everybody. 1. Because your first ball is by definition new. So, what about L2? What's the probability that you get a new ball as opposed to the first ball you drew? I've got n balls. What's the probability that yeah. N minus 1 over n. I've got n minus 1 balls, distinct balls left. I have a total of n balls. One of them I've already spent. So I've got n minus 1 chances out of n to pick the next novel ball. So if you continue this way, what can you tell me about LJ? Huh? Just do a pattern match. If I've already picked, n minus j minus 1 over n, and 1 minus that. Okay? Each of these is a Bernoulli trial. What's the expected value of L1? Everybody. 1. What's the expected value of L2? Notice this is my P2. This is 1 minus P2. So we're now going through a sequence of Bernoulli trials where even though these trials are independent, just like our original coin flip story that we've been talking about so far, they are not identically distributed. Each new Bernoulli trial is different. As soon as I draw a new distinct ball, the probabilities on these branches change. So what is E of L2? What do you know about Bernoullis that have probability P and 1 minus P? The expected value is what? We talked about this. P. So the expected value of L2 is P2, which is n minus 1 over n. The total wait time is what? So let's draw a timeline. Let's say so on the first one I get a hit. Then let's say I have dud, dud, dud. I keep picking the first one, then I have a hit. Then I have dud, dud, a hit. Right? So this is L1. This is L2. Do you agree? This is L3. The number of cereal boxes that I have to buy, or the number of Bernoulli trials. Yeah. Oh, yeah. Okay, okay. Yes. What I meant was not the L2 here. Thank you for pointing that out. The underlying Bernoulli is, so I'm going to keep L2 here. The underlying Bernoulli has P2 as its probability. What's the expected value of L2 then? 1 over P2. And that is n over n minus 1. Thank you. So now I have a total wait time, if you will, where wait time is the number of cereal boxes I buy, which is the sum of these, right? And how many of these do I have? Is it infinite? Ln, right? Ln. So until I get to the nth distinct coupon. Okay? So what is E of L? How would you compute E of L? What do you know about expectation? It's linear in its arguments. We've already talked about that. So it's E of L1 all the way to Ln, and that's E of L1 plus E of L2 plus E of Ln. And E of L1 is 1. E of L2, you told me, is n over n minus 1. E of L3 is n over n minus 3. And you have n over n minus what? Huh? What's the last term? N over what? 1. And let me rewrite the first term as n over n. And now I can pull out the n. And I write the terms from the right to left. So if I pull out the n, this term gives me a 1. The next term gives me 1 over 2. The next term gives me 1 over 3. All the way to 1 over n. Yeah. I skipped the digit. Thank you. You go from n minus 1 all the way to 1. This is called the harmonic series. And it's got some approximation. Let me write out for n large. Now this part is not as important as the setup of the problem and coming up with the expression. So for n large, E of L is approximately log n. Log n plus some Euler's constant plus 1 over 2n. And this Euler's constant is 0.5 something or other. Let me see. Yeah, 0.5772. Euler's constant. There's a lot of things named after Euler. This part is not so important. The setup of the problem is more important. So it's one layer generalized from the original geometric. With the geometric, you have an underlying Bernoulli. You keep flipping coins. So the independent stays here. Every time you stick your hand in there and drag another coupon, you're performing an independent trial. But every time you draw a new coupon, the next trial, the Bernoulli probabilities change. That's what's different in this problem. And just to give you an idea, if n is 5, then E of L is 11.42. So if you're after 5 coupons, you'd have to buy probably 12 boxes on average to collect all 5. Any questions on what we did? Cool. Now, given the time left, I'm going to skip Poisson for now and go to variance. So let's talk about the variance of random variables. So we've got a random variable whose probability mass function is given by px of x, which is the same as the probability that random variable x takes on the value small x. We've defined the mean of the random variable as the weighted sum of the values of that variable. We've talked about the law of expectation invariance. I can't remember if I gave it a name, but let's give it a name now. Expectation invariance, which is that if I take a function of the random variable g, instead of figuring out what the probability law is for g, I can simply plug g in the definition and figure out its mean. So this stuff we've done. Now, we talk about the variance of a random variable, and there are different ways of writing it. So some people write it as var x, some people write it as sigma x squared. It's defined as the expected value of x minus its mean squared. So it's the mean of the deviation squared from the mean. How far does the random variable spread out from its center of gravity? So the wider a probability mass function, the larger the variance. The narrower a probability mass function, the smaller its variance. What do you think the variance is of a deterministic number? Huh? 0. There's no spread. It's a single lollipop of height 1. So the variance is 0 for a deterministic number. All right. The square root of this is called the standard deviation. The bane of your existence. If my random variable is measured in meters, what's the unit of the standard deviation? Huh? Meters. What's the unit of the variance? Meters squared. So you've got to pay attention to that. The standard deviation is measured in the same units as the underlying random variable, and the variance is the square of that unit. Now, what I want to do is actually expand this using the linearity of expectation. So if I were to expand what's in the square brackets, I have a difference of two terms squared. So how do I expand that? What's the first term? X squared. Let's see how much your high school algebra teacher or middle school algebra teacher taught you. No, not 2x. Minus 2x, people. Minus can cause a crash of a plane or the collapse of a bridge. You gotta be careful with your pluses and minuses. Plus e squared of x. Okay? Now, I keep exploiting the linearity of expectation. So the first term is e of x squared. Minus 2, let's not bring out the 2. You tell me how to write the second term. 2x e of x plus e of e squared x. I've simply applied the linearity of expectation. This guy here has a name. It's called the second moment of x. Not so important right now. How do I simplify this term? What do you know about e of x? What do I do with the 2? Take it out. What do I do with E of x? Is E of x a random quantity? No. The mean of a random variable is a deterministic number. Once you know the probability law, or you have some other way of figuring out the mean of a random variable is fixed. It's done. It's the center of gravity of the probability mass function. So I can treat that exactly the way I treat the number 2. So I have 2e of x times e of x. Yay! And what about this last term then? If e of x is deterministic, what can you tell me about e squared of x? So the expected value of a deterministic quantity is the quantity itself. Okay, this is a subtle point. You've got to be very careful with this. The expected value of a random variable is a deterministic quantity. There's nothing random about it. The variance of a random variable is also a deterministic quantity. There's nothing random about it. So now we have e squared minus 2e squared plus e squared. So I have my expression for variance. It's the second moment minus the square of the mean. Okay? That's the variance, and the standard deviation is just the square root of that. Variance is very often much easier to handle algebraically than the standard deviation. And that's why least squares is actually very nice, because you differentiate and you get something linear. But if you have that ugly square root sitting there, manipulating that expression is much harder. Can you tell me for a Bernoulli, we're not done yet, give me 2 more minutes. Bernoulli, I've got 1, 0, p, 1 minus p. This is my random variable x. Can you give me we know what the mean is, right? We've already developed that. Can you tell me what the variance of a Bernoulli is? What's e of x squared? E of x squared is the sum over all x squared px of x. No? How many terms do I have? 2. One of them is 0. So the only term that's left is 1 squared times what? P plus 0 squared times 1 minus p. That 0 squared doesn't give me anything. So the second moment is p. So the variance of a Bernoulli is the second moment minus the square of the mean, which is p minus p squared, which I can write as p times 1 minus p. If I were to plot this, it would look like this. Right? Sigma x squared as a function of p. This would be where? 0. This would be where? And the peak is at 1/2. And the maximum variance is 1/4. So you get the maximum uncertainty in a coin flip in a Bernoulli trial, if the trial is fair. The more lopsided the probability in the Bernoulli trial, there is less ambiguity about the result. Right? If I tell you that this coin flip is very high probability that it's going to land heads, well, I've given you less information. Well, I've given you more information that enables you to determine the outcome. Go away. 2:30, I have office hours. Show up. So go away now, come back in half an hour. Not here. Corey.